Great. So firstly, I'd like to, of course, thank Giovanni and Riccardo for putting together this exciting workshop. And yeah, of course, I'd like to have seen you all in person. And it's very nice to see all these familiar names on the list of participants. But, you know, this is, I would say, better than nothing. And I've seen exciting talks this morning with new stuff that I didn't know about. So I'm also happy to, you know, contribute a little bit from our side. I'm going to today talk in particular about two types of dynamics, and that is I'm going to talk about deterministic individual Skyrmion motion by spin-orbit torques, where we have completely fast and deterministic motion leading to the Skyrmion Hal effect, and then the second part of the talk will be on diffusive dynamics, and finally quite a large part about crystallization on Skyrmions and lattices. So I have to thank all my previous speakers for introducing Skyrmion, so I can jump right in and just want to show you that we can not only generate single Skyrmions, as has been shown previously, but we can also generate quite nicely these Skyrmion arrangements. Let me call them ensembles for the time being, and then later we'll look at the ordering of these. So this was first shown in this paper with a group of Jeff Beach that we did and Peter Fisher. And we could show that you could break up these stripe domains into Skyrmions, and that in contrast to a Skyrmion lattice, where you have a periodicity that is determined by the Jarzynski-Maria interaction at the exchange, here you get some commensurability with the disk radius. So here's a 3x3 and a 4x4 Skyrmion lattice. And these Skyrmions are, as you've already heard, very nice objects, because you can tune their size from the seminal work by Van Joon, where they were more like micron size, to the group at Paris and in Grenoble, where they're smaller, of the order of 100 nanometers. And this slide here was already shown previously, where you can see that there are lots of different Skyrmions with different sizes. And I'd just like to point out here that you can see here in some of these images already there seems to be some kind of arrangement, whereas in other images it seems to be rather random. And if you're interested, there's this nice review by Karin Evershorzeta and Giovanni Finocchio, where you can see more details. Now, by and large, what we have seen today and what I've also discussed up to now has been metal systems, very varying metal systems, but you can also get these Skyrmions in insulator systems, such as thulium iron garnet in contact with platinum. And we actually measured, so this was first developed here in the group by Jeff Beach, and then we recently measured the DMI in this system, showing that the DMI can be actually measured up to relatively large thicknesses of 50 nanometers or so. So even at 50 nanometers of the ferromagnet, we get a sizable DMI. And finally, we can measure these spin structures here also in some kind of arrangement, even not very well ordered. And we can see by current-induced motion that these are chiral Skymions. So this is nice because it means that you can get these objects in a range of different systems. Now, all that I've shown you so far has been 2D systems, where the thickness of our magnetic structure, of our magnetic layer, has been much than the lateral extension of the Skyrmion. But you can also go from 2D to 3D, and this has been some recent work that we did here, in particular Dong-Soo Han and Kyujun Lee, together with some colleagues in Eindhoven. And there's also very nice related work by Amalio and Russell Cowburn, who published this back-to-back with us. And essentially, rather than having a DMI which cans the spins in the plane, we have an interlayer DMI which cans the spins between the planes. And the idea is that then this allows you to have not only a Skyrmion that is confined in 2-dimensional, but actually a Skyrmion that is confined in 3-dimension, where you have a rotation going from up to down as well as left to right. And this is then rather nice because it would allow you to stabilize these type of 3D structures as drawn here, and maybe use them in a complex arrangement in 3D. And the nice thing is that in 3D, you can actually have interactions between particles with many, many more neighbors than in 2D. In 2D, just from graph theory, you know that you can only on average interact with 4 neighbors without crossing the interaction path, which in 2D is then, not possible. But in 3D, you can actually have many, many of these particles talk to each other, and this potentially could realize a huge interconnectivity that is given in neurons in the brain in 3D, which actually have interconnections to tens and thousands of other neurons. Okay, so I just wanted to briefly introduce that this can also be done in 3D, but let's go back to the 2D skyrmions. And here we just developed some material stacks which allow you to move these skyrmions on a relatively regular basis back and forth at speeds of the order of 100 meters per second. And we found that these are also strongly temperature dependent. You can make them in certain multi-layer stacks to be quite strongly temperature dependent. And then the next step was rather to do these before-after experiments, to do real-time experiments. And you might know this video here, which is a real-time experiment where we actually move 5 of these skyrmions back and forth. In reality, this is a few nanoseconds, the movie. And you can see, as this was taken in a pump-probe regime, that these skyrmions actually move back and forth 10 billion times completely reproducibly. If only once such a skyrmion would have gotten out of sync by being pinned or something like that, we would just see gray contrast. So the fact that we see these nice skyrmions moving back and forth means they do this 10 billion times completely reproducibly. And what we also see is, if you look at the current direction compared to the motion, that they don't move along the current flow, and this has already been discussed in some detail. While they actually react to the current instantaneously, so there's very little delay, very little inertia here. The motion direction is along a so-called Skyrmion Hal angle. And now the Skyrmion Hal angle, this was predicted already a long time ago, and was predicted to depend on the size of the skyrmion and on its spin structure. However, we also found that it was dependent on the velocity, and that was surprising. And this was found by Wan Jung and us actually concurrently, independently in different systems. We then published this back to back. However, what we also found is that if we look at the creep and the viscous flow regime, we get both times the dependence of the Skyrmion Hal angle on the velocity, but there is a different slope. We see a rather steep slope in the creep regime, and then we see a smaller slope in the viscous flow regime, which then told us that probably there are different origins of this slope here and the slope here. And I should point out that now this is a rather active field. So after these first 2 works by Wan Jung and us, there was this paper that just came out a few months ago where we looked at more details, and then also the group in Leeds and then France and the Reichert family contributed various aspects to this Skyrmion Hal angle, which is now quite an active topic of research. But coming back to the question, where does this different slope in the creep regime and the viscous flow regime come from? We did some micromagnetic simulations, and here I'd like to point out the contribution by Jonathan in Ghent, who did most of these simulations together with Kailitius. And first they simulated a perfect system with no pinning, and then they see the Skyrmion Hal angle is rather independent of the velocity, in contrast to what we observe. And if they then introduce pinning, you actually see that you can reproduce also these 2 different slopes, large slope here and a smaller slope here. And so this then reproduces our experiment, but let's see what is the origin of these different slopes that we find also in the simulations. Well, if we look at the shape, we see that initially we have skyrmions which are round, and then as we increase the speed, they get strongly elongated. So there is an effect that the skyrmion is not round anymore, but it becomes elongated. And let me just then explain why this leads to a change in the Skyrmion Hal angle. Now, if you look at the skyrmions when they are moving, then you can see 2 things. So firstly, in a perfect system, you can see that the domain wall has changed its shape. You see here at rest, all the colors which denote the magnetization direction in the plane are equally well distributed. So this is a perfect Néel domain wall of the skyrmion. But now you see here there's only very little blue left, and that tells you that now the domain wall has been actually changed. Additionally, we see in particular if we have a non-flat energy landscape, we see the skyrmion at rest relatively round, but then when it moves, it gets elongated. And so we have this mechanism where if you look at the skyrmion at low speed, it's, it moves through some pinning sites and deforms a little bit and grows, but otherwise stays round. And at high velocities, you can see that it elongates. So you'll see this simulation will start in a minute as a round skyrmion. And then after a few nanoseconds of motion, it actually has turned into this ellipsoid. So you get two different types of changes of the spin structure. You get a change in the domain wall, and you get a change in the shape and elongation. And so to check what plays a role, what we did is we varied the torques that are acting. So we varied the damping lag and the field-like torque. And here we vary the field-like torque, which is 3 times the damping, only damping like torque, and -3 times the damping like torque, so just different sign. And we see that in the low speed regime, there is little effect, but in the high speed regime, there's actually a difference telling you that you actually have an impact of the field-like torque on the Skyrmion Hal angle. And this is even for a perfect system without disorder. And this was then reported in the paper here and here. And so overall, we actually find 3 types of origins of the Skyrmion Hal angle that impact the Skyrmion Hal angle in different regimes. In the creep regime, we find these pinning effects, which were first pointed out here by Wan Jung, and the theory was done by the Reichert family. And then we have shape deformations, which then, due to the damping-like torque, lead to a change of the Skyrmion Hal angle with speed. And finally, we have these domain wall shape changes, and there the field-like torque leads to a change of the Skyrmion Hal angle with velocity. So these are 3 different mechanisms which are reported in these 3 papers, and which can explain the full velocity regime from the slow creep regime to the kind of ultra-fast hundreds of meters per second flow regime. And of course, to overcome this, we've already heard you can use antiferromagnetic skyrmions, which were first suggested theoretically by Joe Barker and Zhang et al., and then experimentally was shown by Vincent Cross and Takaki Dohi at Sendai. All right, so this is all I want to show you about this fast motion. Let's change gears and go to slow motion. So here we have a system which is a very low pinning stack, first developed in this paper here, and then recently we have developed this further in work together with Karin Evers-Josette and Uli Novak. And what we see is if we inject current pulses, we can nucleate skyrmions locally here. And there's been some theory here also by Wan Jun's group to locally generate single skyrmions. But we can also see, in addition to the motion to the left due to the current, we also see this wiggling around. The skyrmions don't move on a straight line, but they somehow wiggle around. And this type of thermal dynamics diffusion was actually originally predicted to be suppressed in this paper by Schütte et al. And so to check if this is really diffusion, what we did is we did some tracking of the skyrmions. So I think, did you also, yeah, here, does everyone see the moving skyrmions? Just wanted to check that I'm not losing.
Yes, we can see.
Okay, perfect, great. Okay, good. So we track these skyrmions, and if we then put all the skyrmions initially to the same origin, and then we measure the mean square displacement, so how far they got away as a function of time, you see very nice linear fit, showing this is real skyrmion diffusion. And this could then also actually be reproduced theoretically by Uli Novak's group. They also find this linear displacement of the mean square, the linear dependence of the mean square displacement on the time. And also recently this was reported by Wan Jun's group in this paper here. Now, what can you do with this? There are some nice ideas to use this in stochastic and reservoir computing as suggested in these 2 papers here. And we then realized the Skyrmion reshuffler in this Nature Nano paper. Okay, good. Then let's continue. So something new. Let me just change the laser pointer so you see a little better my my laser pointer. So what we recently started to do is we actually went from skyrmions that diffuse isotropically to anisotropic diffusion. Now, anisotropic diffusion has certain advantages, because if you want to use this, for instance, in a system where you have a path along which you want to direct the Skyrmion motion, it would be a good idea to be able to direct the Skyrmions by some external parameter. So what we do is we actually here break the symmetry by applying in-plane field. And then we see that when we apply in-plane field of just 1 millitesla or 2 millitesla, actually the diffusion in one direction is much stronger than in the other. And here you see actually it goes up to 50% higher diffusion along the field direction than perpendicular to it. The origin is that the Skyrmion actually is not anymore round, but rather is an ellipsoid. It's deformed into an ellipsoid. And this is then possibly useful for token-based Brownian computing, which was pioneered here in the group in Osaka. Okay, so now this is all that I want to show you about diffusion, but thermal dynamics can do much more than single Skyrmion diffusion. If we now increase the density of Skyrmions, we can get the following. What we see is that these Skyrmions actually form lattices. So what I showed you was actually a real-time movie, just looking at it with a Kerr microscope, and over the frame of seconds, you actually form these Skyrmion lattices. And we can characterize these lattices and the amount of ordering by the so-called pair correlation function, which is given here. And then what we can do is we can do a nice FFT to see that, okay, here we have indeed these rings which correspond to the first nearest neighbors and next nearest neighbors, and then maybe you can see a third ring as well. And this allows you to characterize the ordering of our Skymions. And now we do this as a function of time. And here on the left, you see the image. On the right, you see the pair correlation function as a function of time. And what you see is that initially it's rather disordered, but then the first peak kind of grows in height. And this then is this next nearest neighbor distance. And you can also see, if you look down here, that it actually shifts a bit to larger distances. So during this nucleation of the Skyrmion lattice, the average Skyrmion distance also changes. And you can then compare this theory and experiment. You get very nice agreement. And this actually now allows you to determine the interaction potential, which is in our case, the exponent is between 8 and 9. So you have a strongly repulsive potential of adjacent Skyrmions. And now the question is this very nice 2D system, is this useful to actually study statistical mechanics of 2D particles? This was something that was predicted in these two papers here theoretically, and we wanted to check this. And in 2D, statistical mechanics is particularly interesting because you get not only the liquid phase that we know from 3D, which is disordered, and the solid phase in 3D, which is ordered long range, both translational as well as orientational, but you get a new phase, the so-called hexatic phase. This hexatic phase has no long-range translational order, but it has long-range orientational order. And you can see this if you draw these axes. You see there is actually order with the directions, but the distances vary. And the phase transitions between them can be these topological phase transitions. For instance, liquid to hexatic is this Kosterlitz, Thouless, Halperin, Nelson, Young, was predicted to be such a phase transition. And so now we would like to probe this, and in order to do that, we study as a function of time, not the pair correlation function G of R, which is not sufficient to identify the phases, but the local orientational order parameter, which is a measure of how well the system is locally oriented. And you can see that as a function of time, this kind of goes up over the time frame of seconds. And actually for a size 6 absolute value larger than 0.7, we actually get this hexatic phase, as you can see here. So for certain combinations of temperature and applied field, we get into this hexatic phase. And you can see as a function of applied field and as a function of temperature, we see that at low applied field, we get little order, and that's because we have these striped domains. At very high field, we have very few Skyrmions. They also don't order, but at intermediate fields and elevated temperatures, you actually get very good order in this hexatic phase. And that's something which you can also visualize. Here is now visualized, firstly, the size 6, or the local orientational order parameter, which tells you that everywhere where it's dark blue is high ordering. yeah, close to 1, so the average is 0.7 something. And here you can see the domains. So the color gives you the local orientation of the skyrmions. And you see in all the green domains, the orientation is along 20 degrees, in the blue domains it's along 40 degrees, in the red domains it's along 60 degrees. And we see that this nucleation occurs by the crystallization of crystallites of the order of 20-30 skyrmions. And that's something that I found very cool. You can look at the crystallization of a lattice. And you see also here for the less ordered case at lower temperatures, we see there are very, very small domains. In general, the ordering is very poor. And the actually telltale our smoking gun experiment to get the hexatic phase is to look at the decay of the spatial correlation function as a function of distance, because that actually should be in the liquid phase in exponential decay, in the hexatic phase in algebraic decay. And here I should do some advertising for this paper by Huang et al., who showed very, very nice data where you can see in copper oxide, selenium oxide, that for certain applied fields, you get this exponential decrease, which is the liquid phase, and then up here you get very clearly this algebraic decay, which is then the hexatic phase. So this, I think, is a really nice experimental demonstration of this. And what they could also do, they could then extend the phase diagram of this copper oxide, selenium oxide, in addition to the typical conical ferromagnetic, paramagnetic, and helical phase. You actually get not only the Skyrmion lattice as a solid, but you get the Skyrmion lattice as an hexatic phase and the Skyrmion lattice as a liquid phase. And if you're interested, have a look at these 3 papers, our work, their work. They were a bit quicker, and there's some really nice data. And here's also news and views from our side. And I think this is super exciting because we've now taken the next step, and that is we go beyond the studying single skyrmions, but use skyrmions as a model system to study phases and phase transitions in 2D. And of course, next we want to make a movie of the crystallization process. Now I'm done. The most important slide, as usual, I didn't do any of this work. This was done primarily the people that you see here. In particular, also Hartmut Zabel, Martin Jordan, and Gerhard Jakob. This is the group. And then we have great collaborations. Originally, all the work was done with the group of Jeff Beach at MIT, theory with Uli Novak. We work with, for theory with Jonathan Lilliard, Bart van Weinberg in Kent, not Leuven, and people at the Beamlines and Peter Fischer. Then we work with people at the MPI in Stuttgart and Stefan Eisebit in Berlin. In Mainz, we have a good collaboration with a group of Karin, Hyro, and Yura. And of course, the 3D Magic Consortium. Nikola Kislev has been very instrumental in this, Stefan Blügel, Rafael Dudin-Borkowski, and Theo Rasing. And we work with Oleg Tretyakov also. And also nothing would work without the funding, so I acknowledge support by these organizations, in particular our 3D Magic grant. And so to sum it up, so the DMI stabilizes chiral spin structures with a defined topology in metals and insulators in 2D and 3D. Skyrmion motion due to spin orbitals leads to the Skyrmion Hal angle. There are multiple origins that we and others identified. And then we can get thermal dynamics of the skyrmions and use this for non-conventional logic. And recently we've shown that we can actually have skyrmion crystallize in a lattice. And we study these topological phase transitions in 2D. And there are 2 reviews if you're interested to look up some of the work. And with that, I thank you for your attention.